So now we've got Sebastian from the University of Stuttgart, who's going to talk about multipars.
Yes, so my name is Sebastian Hasler from the Institute of Information Security at the University of Stuttgart in Germany, and I'm presenting Multipars, Reduced Communication MPC over Z2k. So Multipars is an offline phase and Rust implementation thereof for the Speeds MPC protocol. So let's first take a look at the existing Speeds MPC protocol. This is a multi-party computation protocol, and in this talk I focus on two parties, Alice and Bob. And the protocol consists of an offline phase, where the parties, for instance, choose secret MAC keys. We have seen this also in the from passive to active security talk. This is for this dual execution. And they also compute some other correlated randomness, which I will mention later. And then in the online phase, the actual input-dependent computation happens. So in this computation, all inputs and intermediate values are secret shared and authenticated using the secret MAC key, and we denote this by double brackets. And if the parties want to add up two values, then this can just be done locally. But if they want to compute a multiplication between two values, that's a bit more complicated. And for that, we need correlated randomness from the offline phase in form of so-called beaver triples. A beaver triple is a triple A, B, C of secret values, where A times B equals C. And then this can be used as a mask to mask these inputs to the multiplication and then reveal these masked values, and then the parties have everything they need to compute a multiplication. So though I don't go into details about how this works in the online phase, but now the question is, how can we produce such beaver triples? And because we need one such beaver triple for every multiplication gate, how can we compute many such beaver triples? And how can we do it efficiently? And so here, that's again the definition. And of course, there has been a lot of research going on how to do this. There are oblivious transfer-based, linearly homomorphic encryption-based, or somewhat homomorphic encryption-based protocols. Also, these protocols differ depending on what is the domain we want to compute on. So the domain could be a finite field ZP for some prime P, but it could also be Z2k. And this is what we focus on in this talk, because it enables a more efficient online phase, as we can use native machine instructions. As you can see here, there is a lot of related work on how to produce beaver triples in these different settings. And I want to focus, or this work wants to focus on setups with a low number of parties. And in this case, this low gear 2.0 is the most efficient protocol when it comes to the communication required to produce beaver triples. However, as you can see, there's a gap right here, because this protocol had not yet been generalized from the prime field setting to the Z2k setting. And this is where my work, or our work, Multipars, comes in. And of course, this is published in PATS 2024. So let's first look at the basic building block of this low gear protocol, which is this linearly homomorphic encryption-based oblivious linear evaluation, so OLE. What is this? OLE means we have Alice's input A and Bob's input B, and we want to compute additive shares of the product A times B. And using linearly homomorphic encryption, this can be done by the goal is to have additive shares of A times B. So this can be done by Alice encrypting the value A, sending this encryption over to Bob, who then performs computes the ciphertext for A times B minus E, where E is Bob's share. Bob sends the ciphertext back, and Alice has the secret key with which this ciphertext can be decrypted, so she decrypts it and obtains the share D. So now we have additive shares of A times B. Okay, and then in this overdrive low gear 2.0 protocol, this OLE is used as follows in order to generate beaver triples. So from the offline phase, or from the beginning of the offline phase, we have a fixed MAC key alpha, okay? And then also every party chooses their own share of A and B. So we already have A and B, but we still need to compute C as the product of A and B, and we need to authenticate all these values using multiplication by the secret MAC key alpha. And this is done by using pairwise instances of the OLE protocol in order to first authenticate the value B. So we compute B times alpha and obtain alpha times B. In the actual protocol, we obtain shares of alpha times B, of course. And then we also use an amortized version of the OLE protocol in order to compute 3 more multiplications. All of these multiplications are multiplications by A, which is why it can be amortized. And after that, we have all the values which we need. So we have C as the product of A times B, and we also have all the authenticated values. And in order to check that nobody tampered with the computation, there is a MAC check in the end, which then basically outputs our authenticated shares, where we can be sure that they are correctly authenticated. However, as this is only secure over finite fields, such as ZP for prime P. If we work over a ring, so let's say modulo 2 to the power of t, then there is an attack due to the fact that we have 0 divisors. So in the OLE protocol, a malicious Bob could add another term of a times 2 to the t minus 1 here, and then in the Logia protocol where this is used, this would then have the effect that Alice gets an additional term right here, and depending whether A0, which is Alice's share of A, is even or odd, this has different consequences. So if A0 is even, so it's a multiple of 2, then that means this is a multiple of 2 to the t, which gets cancelled out, so this attack would not have any effect. And on the other hand, if A0 is odd, then the MAC check in the end fails. So this is a selective failure attack right there, and means that Bob can learn the least significant bit of Alice's share of A. And in a more general form of this attack, Bob can learn multiple of the least significant bits of A. So how did we fix this? Of course, I would not present here if we didn't fix this somehow. So the idea is, first note that we want beaver triples over a domain that looks like this. So here we have Z2 to the k plus s. This plus s has to do with the fact that, with other security reasons, for the max to be secure. But let's say this is the domain where we want to compute beaver triples. And what we do instead is we first compute beaver triples over a slightly larger domain where we have an additional s bits using the protocol which I just presented. And in this protocol, some of the least significant bits might have been leaked to the adversary through selective failure attacks. But then afterwards, we run our new so-called truncation protocol to cut off these least significant bits of the beaver triple. So we obtain beaver triples over our originally intended domain, and they contain no bits which might have been leaked. So this is then secure. Of course, we also did a security analysis. So in the original Logia protocol, the security analysis was based on the security notion of the encryption scheme, which is called enhanced CPA security. And it was shown that this security notion cannot be achieved over for encryption schemes with plaintext space Z2k or Z2t. However, we did a slight adaptation to the security game, and we call this 2S enhanced CPA security, and we showed that this is possible to achieve, and that this is a security notion that is fulfilled by the BGP encryption scheme under common assumptions. namely linear target malleability. Of course, our original goal was to reduce the communication complexity compared to previous work. So now that we have a secure protocol, we did further optimizations, namely using adaptive packing. We use different packing techniques for different parts of the protocol. Packing here means how are the plain text packed into ciphertext, and here for this part of the protocol, for this OLE, we use a different packing technique than for this amortized OLE. Then also modulus switching inside the OLE protocol. Before Bob sends the ciphertext back, Bob applies modulus switching to the ciphertext to reduce the size of the ciphertext. This is only that the size is reduced and we have less communication. And we also use zero-knowledge proofs with rejection sampling. I omitted the detail that in this protocol we also need zero-knowledge proofs to prove the correctness of the ciphertext, and we use zero-knowledge proofs with rejection sampling here, which also reduces the size of these proofs. And these optimizations together mean that the total amortized communication of our protocol in the two-party setup compared to prior work is more than twice as good as the previous best protocol in the same setting. And we also implemented our protocol in Rust. The only other available open source implementation is the one of Z2k. And here you can see that our protocol Multipars, which is blue here, can outperform Z2k, especially if the bandwidth is restricted, which you might want to do in the cloud where traffic is expensive. And at the same time, of course, the communication cost incurred by Z2k, by Multipars is way lower than Z2k, as we have seen on the previous slide. Okay, so thank you for your attention. Here I also have the link to the PETS publication and the implementation, of course. And now I'm happy to take any questions.
Do we have any questions for Sebastian? Yeah, over there.
I can directly ask. I just want to know, is your implementation view if we incorporate to MPCs? Will your implementation be incorporated to MPCs framework?
No, it has not yet been incorporated to MPCs, and there are currently no such plans. This was up to now purely a research effort, but maybe if some company would be interested in using it, then one could do something like this.
You mentioned amortized cost. What is it amortized over?
The amortized cost per triple produced means we cannot produce a single triple because in the ciphertexts we pack many plain texts, like thousands of them, and also the zero-knowledge proofs in the OLE protocol are amortized over multiple ciphertexts. And so we produce Vivo triples in batches of many thousands, and this is why we speak of amortized cost. So we divide the cost by the number of triples produced.
Which zero-knowledge proof did you use?
We used a variant of the top tier zero-knowledge proof, but with small optimization where the number of values that need to be sent is reduced from 4 to 3, and with this rejection sampling idea.
Okay, thanks. Well, thanks to the speaker again.